What's going on, everybody? In this video, we're going to be talking about how to evaluate limits algebraically. More specifically, we're just going to start off here by talking about when limits get interesting, right? There are specific cases of limits that you're going to see and that you're going to have to do as practice problems, right? And they're going to be much weirder, and you're not going to be able to use things like test points, right? So here I'm talking about indeterminate cases, right? When you get like a 0 over 0, if you try to plug in the number, if you get an infinity over infinity or an infinity minus infinity or whatever, right? We're going to talk about these indeterminate cases, and we're going to talk about the three main types of solutions that you're going to be doing. And we're going to do plenty of practice problems there, right? So we'll talk about factoring. Okay, that's one of the main ways to solve, right? And I'll talk about when you actually go about factoring and what your tell is, all that stuff. We'll talk about simplifying, right? We'll talk about finding common denominators, which is a huge thing that a lot of people get confused with. And then we'll move on to rationalizing. That's when you have square roots in your limits and you have to deal with that, and it gets really gross. Okay? So we'll be doing all that in this video. Now, I quickly wanted to mention I do have a full Calculus 1 course that you can go check out in the description down below. In this course, basically what I do is I do additional practice problems for each video that I make on the YouTube channel for Calc 1, right? So I have all these extra videos for you to pick through, do all these practice problems for, and I have reviews, I have all that stuff, and it also just gives you a better chance to talk to me one-on-one, and we can figure out, what you're having trouble with and all that. So I hope you consider checking that out in the description down below, and let's continue on with this video. So let's begin here with our red section, okay? This is when limits get interesting, right? And so I start this off by saying that we could really care less about the limit as x approaches 2 of x cubed plus 2x. Now, why do I say that? Well, if you have, let's say that x cubed plus 2x looks something like this, right? It's going to look something along those lines. And if you try to find what this limit is as x approaches 2, right? Meaning, let's make sure we all are on the same page of what this means here, right? We're trying to see that as we get closer and closer to x equals 2 from both sides, right? So as we approach x equals 2 from this side and this side, right, along the curve, what is the value of y? What is the value of y? And remember, this is y, this expression, right? You could set y equal to x cubed plus 2x, and the value of this is going to be what your y is. Okay, and so we're trying to see, what value of y we are approaching as we get closer to x equals 2, right? But for a polynomial, I mean, this thing is completely continuous, right? There's no, infinite discontinuities or anything like that that we need to worry about that would screw us up. And so, to find this limit, we can just plug in 2, right? We can just plug in 2 and because we're going to be approaching that point. So that really isn't helpful for us, right? There's nothing new that's learned here. Okay, we could just, this is plugging into a polynomial just like you did in algebra. So seeing that there's no new insights here, things will only start getting interesting when we get a 0 in the denominator, right? That is when we start to care a little bit, because when we get a 0 in the denominator, right, we can get different types of discontinuities. Okay, we can get infinite discontinuities, we can get removable discontinuities. It all depends what kind of case we have. Okay, and so getting a 0 in the denominator or getting a case like that where you have an indeterminate form, I mean, that's where limits actually come in handy a lot more. Okay, and so how we originally dealt with these limits, okay, was we used test points, right? And that was in my previous video, the intro to limits video. And what we did was we just said, okay, well, here we see that we'd get a 0 if we tried to plug in 3, right? This is the limit as x approaches 3. If we plugged in 3, we would get a 2 times 3 over 3 minus 3. That's a 6 over 0. We can't have that, right? And so we used test points. We said, okay, well, as we get closer to x equals 3, right? Let's say from the left side, right? So if we had like 2.5 minus 3, right? So we're getting closer. This becomes negative 0.5. If we have like 2.9 minus 3, that's negative 0.1. And as we get closer, right, this number gets smaller and smaller and smaller. It's also negative, right? And so what happens is, well, this entire fraction, as x approaches 3, from the negative side, right? So we would have to put a negative side there. And the reason for that is because we're on the left side of 3, right? These numbers are to the left of 3 on a number line. Okay? But, that is going to blow up the entire fraction. It's having these little numbers like this, right? Having a little number in the denominator will give you a big number overall. And so this thing goes to negative infinity. Okay? If you looked at 3 from the positive side, you would get positive infinity. Okay, because these numbers would now be positive. You'd be dealing with like 3.5, and you get my drift. Okay, so this is all review. Okay, but somewhere where we can't use test points is something like this. Why? Because we get an indeterminate form. Okay, if we plug in 1 here, we not only get a 0 in the denominator, but we also get a 0 in the numerator. Okay, and this is a problem, because if we try to look at, and you can try this, if you try to approach 1, right, from one side or the other, you end up seeing that, well, both of these are going to 0, so how do you actually know what's going on? Okay, and so using test points is really obnoxious in this case, and you probably can't come up with a good answer. Okay, so what we're going to do is we're going to talk about how we can actually solve those cases. And that's in our next section here on indeterminate cases. So, how do we deal with these cases where we can't use test points? Well, there's 3 main methods. And those 3 main methods are factoring, simplifying, and rationalizing. Okay? For factoring, that's for example like this, right? Where we have the limit as x approaches 1 of x squared minus 1 over x minus 1. That's what we just saw. Notice that you could break this thing up, right? This is difference of 2 perfect squares. You could break it up into x minus 1 and x plus 1, right? And then, if you did that, you could just cancel x minus 1s, and you'd be left with an x plus 1. Now, I know that's a lot to keep in your head right now, and I don't expect you to. It's fine if you can't, right? Because I probably wouldn't be able to anyway. I will show you that, and we'll do a full example where I do the factoring method, okay? But we can get rid of this x minus 1 in the denominator and thus get rid of the over 0 problem. Okay, that's what I'm trying to get you to get out of this. Now we could also do some simplification, right? And most often that simplification is by finding common denominators, right? So, here if we found common denominators, okay, we do a little bit of simplification, and we'll do an example with this later. We can get rid of this over 0 in the, we can get rid of the 0 in the denominator, right? We won't have to deal with it anymore. And you'll see that. It's kind of interesting how simplifying here is going to allow you to get rid of something down here. Okay? Again, you'll see that and you'll understand more of what I'm talking about. But just know that, simplifying here, finding common denominators, combining this will help you out. Now, there's also rationalizing, and that is getting rid of the radicals in the numerator. Okay, because you'll end up with a bunch of limit cases where you get radicals in the numerator, and what you can do is get rid of them, put them down in the denominator, and you can get something in the numerator that is completely free of radicals, which allows you to cancel some stuff. Like in this case, we'd be able to cancel x squareds if we get rid of the radicals. You'll see more about how that actually ends up working, and we'll talk about it. Okay, so that's an overview of what we're going to be doing in this video. Let's talk about that first method, which is factoring. Okay, so let's look at that example from before. You see that we have the limit as x approaches 1 of x squared minus 1 all over x minus 1. Now, how do you deal with this? Well, again, I was talking about factoring here, right? And this is a difference of perfect squares, right? As a recap, a perfect square is something that you can take a square root of and get a nice number out of, right? So x squared is a perfect square, 1 is a perfect square, the square root of 3 is something gross, and so that is not a perfect square. Okay, and when you say difference to perfect squares, you just mean that you are subtracting them, right? And I just said that because I know a lot of people actually aren't 100% sure what a perfect square actually is, so there's a little refresher. Now, we can factor this, and so we can write this as the limit as x approaches 1 of x minus 1, x plus 1, all over x minus 1. Here, you can see that we can cancel, right? We can cancel the x minus 1s, and so we're left with the limit as x approaches 1 of x plus 1. Okay, this right here is something that we can plug into, just like we had with that example in the red section, right? The polynomial, right? We can plug in this limit. We can plug in the 1. And so when we do that, we just get, we're plugging the 1 for x. We get a 1 plus 1. This is the hardest part of the problem. This is 2. Okay? And so, that's that. Okay? You get a 2 there. And that's what this limit ends up equaling. Now, what that means, okay, if you're following with the idea of what limits are, right, is that you're going to have some x squared minus 1 over x minus 1 graph. I'm assuming it's going to be kind of like linear, right? And as you approach x equals 1, right, so let's say the graph looks something like this, right? And let's say this is x equals 1. This might be a weird way to look at it. So let me actually draw this out. Okay, so let's say that you're at x equals 1 and you have that graph, right? And the reason why I'm drawing a line is because you have an x squared divided by an x, and so I assume that you'll get something that's a line here. And so what's going to happen is at x equals 1, there's going to be an open circle here, and that's going to be at y equals 2. Why am I saying that? Well, that's because you have a limit that is defined here from both sides. That means, recall from one-sided limits, that the limit from the left agrees with the limit from the right. And so these values are approaching the same exact thing. They're approaching y equals 2 as they get closer to x equals 1. Okay, so you end up with a removable discontinuity here. Okay, we'll talk more about that, so don't worry if that's a little fuzzy with you right now. So our next problem is more or less the same idea. There's just going to be a little more work involved because now we have to factor both the numerator and the denominator, and the denominator is kind of gross to factor. Okay, so what we're going to do here, right, we'll start off by just in the same exact way. Right? We see that we have in the numerator a difference of perfect squares, and so we are going to factor it as such. This becomes x minus 3 and x plus 3. Now the denominator is a little tricky, okay, because nobody likes to factor things where you have like a something other than 1 out front here. Okay, I hated that when I was I still hate that, right? So my favorite way to factor like this, I mean, you can use the quadratic formula, and if you're comfortable with that, definitely go for it. I like to use the AC method when I see bigger numbers here, like I see a 7, and I don't want to have to plug all that through the quadratic formula. So a quick refresher of the AC method for those of you that aren't too familiar is what you're going to do is you split up the middle term and you make 2 groups. Okay, and so you're going to split up this 7x into 2 numbers that add to be 7x, right? So you don't change the value of this quadratic. And they have to multiply to be a times c, right? In a quadratic, which takes the form ax squared plus bx plus c, you want the number that multiplies to be a and c, hence AC method, and adds to be b. And so we'll go ahead and do that, right? What are 2 numbers that add to be 7 and multiply to be 2 times 3, which is 6? Well, that is 6 and 1. And so we can just put the 6x here. Doesn't really matter which way we go with it, but we'll put the 6x there and the x there. And so what we're going to do is we are just going to start factoring. We'll divide this into 2 groups. we can factor a 2x out of the first one, and we're left with an x plus 3. And then the next one is an x plus 3. And so this is essentially like a 1 times x plus 3. Right? And so we can factor a x plus 3 out of both of these terms. Right? Just like we factored a 2x out of these two terms. Right? We're factoring an x plus 3 out of both of these. And we get a x plus 3 times a 2x plus 1. Right? And that's why I put the 1 there, was to make it more obvious that this is going to be a plus 1. So then we get x plus 3, we get 2x plus 1, and that's relatively quick when you get used to it. And for me, that can be quicker than quadratic formula. Okay, so now you can see that we have the x plus 3's canceling off, right? And I won't draw a line through it, so you can, actually still see what's there. I don't know, maybe you like that method of crossing out better. But now that we factored, we can see that we've allowed ourselves to be able to plug in the negative 3. Right? Check this out. If we plug in negative 3 now, we don't get a 0 in the denominator. We also don't get a 0 in the numerator. We get a negative 3 minus 3 over a 2 times negative 3 plus 1. That is a negative 6 over, this is a negative 6 plus 1 is negative 5. And that is 6 over 5. Right? And so that is our answer for our second example. Okay, so that's all factoring really is, right? When you get a limit that's really weird, you can't use test points on it, right? You're getting an indeterminate case where you have a 0 over 0, infinity over infinity, whatever, right? This is a quick and easy way to just kind of like chill out, right? And do this limit. And so, yeah, that's factoring. Now let's move on to simplifying. Okay. So this is the first example that we had brought up in the blue section. Okay, we were talking about simplifying. We were talking about finding common denominators, right? And that's what we're going to have to do here, right? We can see here that we can't factor this. Like there's nothing we can do to factor. Okay, but what we can do to make this look a little nicer is find common denominators between these two, and then be able to do that subtraction and get something that's all in one fraction. Okay, so let's go through the process of finding common denominators. I know that can be a bear, but we got to get through it. Okay, so just focusing on the numerator here. This is 1 over x minus 1 over 3. We can say that our common denominator here is going to be 3x, right? We can just multiply them by each other because there's not much else we can do. So if we multiply this piece by 3 over 3, we get 3 over 3x. We multiply this piece by x over x, we get a x over 3x. Putting that together, we get a 3 minus x over 3x. Okay? And so we say that this is the limit as x approaches 3 of 3 minus x over 3x all over x minus 3. Now, if you know your fractions well, you might be able to see something nice that we can do here. We can actually move this piece right here. Why do I say that? I'm not just going to do it. I'm going to tell you why we can do it. Right? If we have 1 over 2 all over 3 over 4, right? This is the same thing as 1 over 2 divided by 3 over 4. Right? That's the same idea. And hopefully either keep, change, or stay, change, flip how we divide two fractions. We just do 1 over 2 times 4 over 3, right? We flip this fraction. And that's how we can end up seeing that this 3 piece right here, because you can think of this as x minus 3 over 1, right? That correlates to 3, that correlates to 4. That 3 piece can just be written as being multiplied by the 2 piece, right here. And so that is how you can rewrite this limit to make it look a little nicer. So you can write this as the, hopefully I didn't give myself enough space at all here. The limit as x approaches 3 of a 3 minus x over a 3x times x minus 3. Now, you'll notice that these two are strikingly close, right? You have a 3 minus x and an x minus 3. These are opposites of each other, so you know the 3 is positive here, but it's negative here, and the same thing for the x. It's negative here, positive here. So what we can do is we can factor out a negative out of the numerator and rewrite this as the limit as x approaches 3 of a negative x minus 3 over 3x times x minus 3. Then we can cancel, and we can write this as the limit as x approaches 3 of a negative 1 over 3x. Right? And then we just plug in the 3, and we get negative 1 over 3 times 3, which is negative 1 over 9. Sorry if I went a little too fast at the end there. Basically what we did was we factored out a negative here to turn this from a 3 minus x into a x minus 3. That allowed us to cancel. And then we just plugged in our 3. Okay, and we got a negative 1 over 9 from that point. Okay, so hopefully that makes sense. I mean, really here, that was just finding common denominators, and that, like factoring did, allowed us to get rid of that 0 in the denominator, right? It allowed us to manipulate our indeterminate form into something that we could actually find the limit of. Okay, so we're going to see a couple more examples here. We have 2 more of simplifying, right? Another is a common denominators example, which you can't get enough of that practice because that can be really annoying. And another is what you're about to see, which is just simply expanding a limit. Okay, or expanding like a piece of a limit, right? So for this case, right, we can't, I mean, this has already been factored, right? There's no factoring we can do here. Like we have a 3 plus x squared. That's, you can think of that as being like a factored form of whatever quadratic you would have had if you would have expanded that. Okay, there's no common denominators to find here. And it really looks like the only thing we can do here is just expand this 3 plus x quantity squared. So let's do that. If we expand the 3 plus x, right, remember this is 3 plus x times 3 plus x. I might be getting a little too basic here, but so, you know, let me know if that's how you feel. but yeah, so we get a 9. We're going to get a 6x, it looks like, and then we'll get a x squared. We'll get a minus 9, and we'll get a over x. Notice here that the 9's go away, right? The 9 will cancel off with the negative 9. And from there, we get something that we can simplify, right? We get another simplification that we can make. We can cancel off the x's. So we cancel off an x here, we cancel off the 2, cancel off the x, and we're left with the limit as x approaches 0 of just a 6 plus x. Right? And this, I mean, if we look at the limit as x approaches 0, right, we plug in a 0 here, we get 6. That's our answer. Right? So it's kind of interesting here how we were expanding this in order to simplify later. Okay, that we expanded just so we could simplify later, and I think that that's pretty interesting. Okay, we were able to make massive simplifications just because we expanded, and so that's how we got our answer for that. So be on the lookout for that. If you can't find common denominators, you can't do things with radicals, which we'll see in a second. If you can't factor, you want to probably end up expanding whatever you have, right? Cool. Let's move on to our last example here. These are very common, having like an h, right? We'll see why later when we talk about the limit definition of a derivative. That's for another video. But with that limit definition of a derivative, you often see an h in the denominator, and that h is approaching 0. So what ends up happening is, well, you get a 0 over 0 case, right? If you plug in h equals 0 here, you get a 1 over x squared minus a 1 over x squared, that's a 0. Okay, and so you get one of these indeterminate nasty cases, and so what do we do now? Well, we have things that we can find common denominators with, right? There's no factoring, there's no expanding, right? There's nothing we can do here other than finding common denominators. Okay? And that's how you check. If we start finding common denominators here, and I guess I can just start writing this out as a limit. Okay? Last time I kind of just took the numerator aside. But if we start off with this, we can make this look a little nicer just like we did before, where we can just put the h here and we can put it here. Okay, that's for the same reason as before. We can write this as 1 over h times x plus h squared minus 1 over h x squared. Okay, that's something that I mean, you don't have to do that, but I don't want to have like multiple fractions to deal with. So, you know, that's something you can do primarily, or prematurely if you'd like. So I'm just showing you another way that you could do this. Finding common denominators, we can multiply this side by an x squared, multiply this side by an x plus h quantity squared, right? And if we did that, let me just show that out real quick. Multiply this by x squared over x squared, and multiply this by x plus h squared over x plus h squared. We get the limit as h approaches 0 of a x squared over h x plus h squared x squared minus x plus h squared over h x plus h squared x squared. We can now combine these. And when we do, we can also expand this while we're at it. We get a x squared, right? That's the first piece here. Then we're going to do minus this entire second piece, which is a x squared. We'll get a, when you expand that, plus 2xh plus h squared. That's going to be all over h times x plus h squared x squared. Okay. So, you know, you still see here that we do have an h in the denominator here, right? We still are going to end up with a 0 over 0 case. And so we haven't done anything yet, but watch what happens when we cancel out an x squared here, because as you'll see, this x squared cancels out with this x squared. Okay, we can simplify this to be the limit as h approaches 0 of negative 2xh minus h squared, right? Because hopefully you can see how this is x squared minus x squared. And I just distributed that negative through to the 2xh and the h squared. Okay, this is all over h times x plus h squared times x squared. You can see here that we can take an h out of everything at this point, right? You can take an h here, take an h there, take an h there, right? And from that point, you just have the limit as h approaches 0 of negative 2x minus h over a x plus h squared x squared. Okay? From here, it looks like we can go ahead and plug in that h equals 0. Okay? When we do that, we get negative 2x minus 0, right? So that goes away. And we get a, this becomes x, just an x squared, right? This is x plus 0 squared, which is x squared. And you multiply it by an x squared, and so you get x to the 4th. And then you can cancel off an x with a 4 here, make that a 3. You get negative 2 over x cubed as your final answer. Okay? And so that is your answer there. Okay? And so hopefully you can see how this is, again, just another finding common denominators. We really didn't do much other than, I mean, once we found common denominators, we just combined that the numerator on one side with the numerator on the other side, and we were able to cancel, so we could cancel out h's, right? We could just cancel out an h on top and bottom. We did that. Everything went well. Sorry about my dogs barking. I don't know what's going on there. But anyway, so that does it for our simplification section. Now let's move on to the rationalization section, which is our last for this video. And if my dogs would just cease barking, that would be fantastic. Awesome. So now we're going to talk about what happens when we get radicals. Right? Radicals are tough to deal with. Okay? And so we need to be prepared. And so what we do when we have radicals is we multiply by a conjugate on top and bottom. Right? Here's the idea with conjugates. We want to get rid of the radical. Right? We know that if we multiply x squared plus 9 by itself, right? We multiply it by the square root of itself. The square roots will go away and we just get x squared plus 9. But here's the problem. That's cool. We can multiply this piece by itself. But if we multiply this straight up by x squared plus 9, we're going to get that radical out of here too. Like if we just multiply that, we would get x squared plus 9 minus a 3 times square root of x squared plus 9, right? And that doesn't do any good for us because we still have that same square root. So we don't want any square roots. And so how we do that is we use conjugates. So the idea of conjugates, right? Let me give you an example of something with conjugates, right? So we can have an x plus 2, right? And we can have a conjugate, which is x minus 2, right? This would be a conjugate of x plus 2 because we have one of the signs of one of the terms being opposite, right? Why is that important? Well, what ends up happening is if we actually multiply these two out, we get a x squared plus 2x minus 2x minus 4. And so the middle terms go away and we're just left with a x squared minus 4. Okay? That becomes useful for radicals. I'll show you that in a second, but notice here that this is strongly correlated to difference of perfect squares, right? The x squared minus 4 is a difference of perfect squares, and when you factor that, you get two conjugates. Okay, so that's interesting. We can expand on that and do the square root of x plus 2 and the square root of x minus 2, right? Watch what happens to the square roots here. Square root of x times square root of x is just a regular x. Now we'll get a plus 2 rad x in there. We'll get a minus 2 rad x in there. We'll get a minus 4. And here you can see the radicals go away. We just get a x minus 4. Okay, so that's really interesting. We can get rid of the radicals. Now, we're still going to end up adding radicals in the denominator here, but you'll see why that actually ends up helping us. Okay, and you'll see how that gets rid of the x squared I mentioned before. So let's multiply by conjugates here. We multiply this by x squared plus 9 plus 3. Okay, we're just going to do that. By the way, I don't think it matters if you did, instead of rad x plus 2 and rad x minus 2, you did minus rad x plus 2. Right, you still end up with the same results. Here you would get a negative x, right? And you would still get rid of the middle terms, right? You would get a plus 2 rad x and you get a minus 2 rad x, and then you get a plus 4. Right, so now you just end up with a negative x plus 4, but the middle terms are still gone. And so, yeah, these two things are still conjugates of each other, but it's nicer to, what we generally do is we do it this way. Okay, so continuing on with what I said, and hopefully not breaking off into another rant, we're going to have that, we're going to have that, and now we're just going to continue on. We're going to do this out. Well, when we multiply, remember the middle terms go away. The first two terms, that gives us an x squared plus 9. Right, the radicals go away. And for the second two terms, the negative 3 and the positive 3, that just gives us minus 9. And on the bottom here, don't distribute the bottom. Okay, we're just going to get a x squared and then a x squared plus 9. and then a plus 3. And notice what happens. We can rewrite this as the limit as x approaches 0 of these 9's go away. We're left with a x squared over x squared. And then this bottom x squared is being multiplied by a square root of x squared plus 9 plus 3. The x squareds go away. And getting a little less sloppy here, this becomes the limit as x approaches 0 of a 1 over the square root of x squared plus 9 plus 3. And here, we don't have a 0 over 0 case anymore. We can plug in, right? We're not going to get a 0 in the denominator. We're going to have something nice. Plugging in 0, we get a 1 over the square root of 0 plus 9, so it's the square root of 9 plus 3, right? This is going to be a 3, so it's 1 over 3 plus 3. That gives us a 1 over 6. Okay, that's nice, right? That's pretty cool. We got rid of the x squared, right? We got rid of that 0 in the denominator by multiplying by conjugates on top and bottom. We got rid of those radicals, and what that allowed us to do is it allowed us to free up a term that we could use to cancel in the denominator, right? So that's what that was all about. We were just freeing something up. Okay, that's why we were freeing up the numerator. That's why we don't want radicals in the numerator. Okay, that's the whole concept with rationalizing. Now we do have one more example for you in this video. It's a little bit of a combination of what we've talked about, and if you want to try it on your own, feel free. Okay, but yeah, this one is a little bit stubborn. Okay, now this is not just about radicals, right? The first step is actually nothing to do with radicals. Okay, the first step, I mean, we see we have two fractions here, right? The first step is to find common denominators. That's actually not as bad as it seems, right? We have a x times the square root of 1 plus x and just a regular x. And so all it seems that we need to do here is multiply this second term by the square root of 1 plus x over the square root of 1 plus x. In doing that, we get the limit as x approaches 0 of a 1 over x square root of 1 plus x minus a square root of 1 plus x over the square root of 1 plus x. Okay? Oh, sorry, x times the square root of 1 plus x. Now, let's just combine, right? That's what we do with common denominators. We get a 1 minus square root of 1 plus x over x square root of 1 plus x. Okay? So now we have a radical case, right? Now we have something that we want to rationalize. We want to free up that numerator. And no, multiplying, doing some conjugate work here, that's not going to nullify or just kind of go backwards with what we've already done here. And I know that might seem what it would do at first, and that's kind of what I thought when I was doing this in Calc 1, or maybe it was pre-calc. I don't, whatever time it was that we were doing limits. I think it was both. So if we multiply by conjugates here, we can just do a 1 plus this time. Where I like to, do the sign flip with the second term, not the first term. That's what I think most people do. Okay, so doing our multiplication here, we are going to multiply the first two terms. We get 1. Multiply the second two terms and get minus, right? Remember that minus here. That's going to be a 1 plus x. Okay, and that's going to be all over. Don't distribute the denominator. This is a x square root of 1 plus x times 1 plus square root of 1 plus x. Okay? And it is important to see here, I do want to note, I'm assuming that, these are conjugates. We know that these are conjugates, and that's why I'm only caring about multiplying this and then multiplying this, right? Usually when you distribute like that, you have to worry about your middle terms, right? Here we know since they're conjugates, the middle terms cancel. Cool. So now you want to notice that Well, if we combine the numerator, the 1's cancel, right? We get a 1 minus 1. We also get a minus x. So we can write this as the limit as x approaches 0 of a minus x all over x square root of 1 plus x times 1 plus square root of 1 plus x. X's cancel. And last time we write a limit of this video, negative 1 over the square root of 1 plus x times 1 plus the square root of 1 plus x. And then plugging a 0 in for x. We get a negative 1 over the square root of 1 plus 0. That's just going to be the square root of 1, and that's 1. So this entire thing just becomes 1. 1 times a 1 plus, again, we get a 1 plus, a square root of 1 plus x, 1 plus 0, right? That's just square root of 1. That's 1. And so this whole thing becomes the square root, or not the square root. This whole thing becomes negative 1/2. Okay? And that is our final problem for this video. So just a quick recap, because I want to make sure you have this all under control. Okay? When we have these indeterminate cases, there are three main methods that we want to use, right? There's factoring, simplifying, and rationalizing. Factoring is when you have to, factor and be able to cancel off. And that's how you get rid of your indeterminate form, right? That's how you get rid of your 0 over 0 or your infinity over infinity or whatever. Okay? And, the factoring can get a little more complicated. You can have stuff like that. We talked about the AC method. That's a really nice way of factoring. We talked about simplifying next, which was, finding common denominators anytime you see fractions, right? That can be really nice. And that allows you to get rid of your denominator. Okay, we also did a more complicated example where we, said that when you have the h in the denominator, we're talking about limit definition of a derivative. We'll get to that eventually, but yeah, same process here, finding common denominators. We moved on to rationalizing, which we dealt with square roots, and the square roots, we wanted to free up that numerator so we could cancel off with the denominator. And how we did that was multiplying by conjugates, which allowed us to actually get rid of those square roots entirely by canceling out the middle terms. Okay. And when we did that, we were able to get rid of those x squareds, and we got a nice little answer of 1/6. Okay. So that is it for this video. I hope it was able to help you. And do remember that I have that full Calculus 1 course in the description where I have plenty more practice problems. I have a whole worksheet for this video and all my other Calc 1 videos where we actually go through these examples together even more so. And it, again, gives you a better chance to communicate with me one-on-one and ask me any questions that you have. Okay? So again, I hope this video helped, and I'll see you soon.